Now, this is the instantaneous position, x of t. X varies with your velocity and with time. If I wanted to know a particular distance, in this case, the total distance between t1 and t2, as v varies with time, then I could say x, let's just say x from 1 to 2 is equal to the integral from t1 to t2 of v sub t d sub t. And if we knew what v was, what the equation for v, and we put it in here and we took the integral of it, and then we plugged in t2 into that answer, and then from that we subtracted what we would get if we plugged t1 into that answer, we would get the total distance. So let's try to work through a simple example of all this mathematical stuff. So let's say you're in a car and you're traveling at a variable velocity, and we're going to draw this velocity again. Get some ink here. This is time. This is velocity. Time 1, time 2, time 3. We won't worry about what the units are. Could be minutes, could be hours. And just for simplicity's sake, we'll say this 10, 20, 30, and I'm going to draw, put a point there, and I'm going to draw a line, straight line right through here. So this is our velocity versus time. It's a straight line. It follows this trajectory. If you remember your basic geometry for the equation of a straight line, we have to find the slope, m. M is delta y, 20, divided by changing your x-axis, which is 3. So our slope here is 6.67, 20 divided by 3. Our initial velocity is 10, so the way we would write this is v sub t for this equation, for this line, equals 6.67 t plus 10. So for any value of t, we can find out what our instantaneous velocity is at that point. So for t equals 0, well, our velocity is, this is our initial velocity, v0, it's just 10. For t equals 1, our velocity is 6.67 plus 10, which is 16.67, and we'll just say this is miles per hour. At hour 2, our velocity is 2 times this, plus 10, which happens to come out to 23.33 miles per hour. At T3, we get a nice even 30 miles per hour. So as time increases, first hour, second hour, third hour, our velocity is increasing from 16 miles per hour to 23 miles per hour to 30 miles per hour. So what does that mean in terms of the distance that we're traveling? Well, you can see our velocity is changing every instant of time. The velocity is different. So what we need to do is take our integral. So x of t equals the integral v sub t dt. Well, we know what v sub t is, right? So we're going to take the integral of 6.67 t plus 10 times dt. When we do that, we find out that x of t equals, and now to evaluate integrals, you just need to look in any calculus textbook. There's a whole bunch of tables with a whole bunch of evaluation of integrals. But for something times t, the integral is that thing divided by 2 times t squared. So 3.33 t squared is what this term integrates to, plus a constant just becomes a constant times t. So x of t equals 3.33 t squared plus 10t. And don't worry about how we got from here to here. Again, it's just tables of integrals out of a textbook. This tells you where you went, in this particular time. It doesn't really tell you where you started from, though. So we're going to add a value here, a constant. We're going to call it x of 0, because we don't really know how far we've gone before we started moving along this velocity trail. So anytime you do an integral, there's always the addition of a constant, because you never know where you were when you started this. In our case, we're going to say we started at 0, so x of 0 actually is 0, and we won't worry about it. But just as a general case, you always add a constant to your integrated value. Now we want to say, well, okay, so how far did we go between time 1 and time 3 in those 2 hours? How far did we go? Well, so we're going to need the integral of v dt from t1 to t2. In this case, it's the integral from 1 to 3 dt dt, and all that means is that we take the integrated value, so x from 1 to 3 is equal to 3.33 t squared plus 10t. We're going to evaluate that from 1 to 3, which just means we're going to evaluate it at 3, we're going to evaluate it at 1, and we're going to subtract this one from this one. So if we do that, we get 3.33 times 9 plus 30 minus 3.33 plus 10. And my handy calculator says 46.64 miles. That's our total distance we went, but what does that look like on a graph? Well, if you know your algebra, you know that this is the equation of a parabola. So if we just go through and plot some points, we'll see that at t equals 1, x equals 13.33. At t equals 2, x equals 33.32. T equals 3, x equals 59.97. And all I'm doing is evaluating this equation for t equals 1, 2, and 3. So if I wanted to plot those, and this is my time scale, and this now is x, and I'll be a little arbitrary here, 20, 40, 60 miles. Then after 1 mile, I'm at 13 1/3, so let's just say that's right there. At 2 miles, I'm at 33 1/3, let's say that's there. And at 3, I'm at up here almost to 60. And if you recall, we assumed that our initial position was 0, so at time 0 we were at location 0. That's just time 0 is here, so this ends up looking like a parabola. So I have a constant velocity, increase in velocity, which means I'm traveling at a constant acceleration. I have a constant acceleration. My velocity is increasing steadily or linearly in a straight line, and my distance is increasing parabolically or exponentially. And I'm saying we have a constant acceleration, but how do we know that? Well, I can go back to my original velocity, v sub t equals 6.67 t plus 10. And I can take the derivative of this, because I know that acceleration equals dv dt. So the derivative, again, it's the opposite of integration, and again, you just go to mathematical tables to look these things up. But if I have a constant times t, the derivative of that is just a constant. And if I have a constant, the derivative of that is 0. So my acceleration is 6.67. And this would be miles per hour squared. In the normal sort of metric world of physics, distance would be in meters, velocity would be meters per second, acceleration would be meters per second squared, or meters per second. So constant acceleration, if I drew this on a graph, it would be a flat line constant at 6.67. That yields a linearly increasing velocity, which yields an exponentially increasing distance. And that's the effect of multiple integrals and multiple differentials. That gives you an idea of how we talk about positions of things, positions of objects. Remember, this started with an object B sitting on my line, a body B sitting on my one-dimensional axis, and then we asked the question, well, where is B? Well, we know where B is. How fast is B going? Well, we figured out how fast B is going. We figured out what the acceleration of B was, and we worked backwards, knowing the velocity of B, how far did B go. We could also, if we wanted to, start with the acceleration of the body B and figure out how fast it was going with time, and then knowing that, how far it went. So these are all simple, basic principles for defining movement of a body in a one-dimensional space. And there are, of course, 2- and 3-dimensional analogies of this as well. We're going to stick with the one-dimensional right now because we have another important concept to introduce, which we'll do in the next video, and that's the concept of mass and force.